Hi, thank you so much for joining me. In this video clip, I want to do a problem on constant pressure calorimetry. At that point, the heat that we gain will lead us, because it's heat at constant pressure, it's going to lead us to the enthalpy of our reaction. So in this case, we have a sample of NaOH, aqueous, and we have a 100 milliliter sample. I always want to list your givens. It will really help you in your problem solving. And 1 molar. And I'm going to add to that sulfuric acid. So this is going to be a neutralization reaction. Again, I have 100 milliliters of a 1.00 molar solution. Right? Now that's going to yield 2 waters. So neutralizations always give you a salt plus water. All right, so that's the heart of this. We are also given an initial temperature of 23.5 degrees Celsius and a final temperature, the maximum achieved once we mixed these solutions in our calorimeter, of 30.10. Now note that this is the temperature change of our surroundings. The bulk solution provides the surroundings for our actual system, which is the neutralization reaction. So in this case, in all cases, Q of my reaction is going to be equal in magnitude but opposite in sign of Q of the solution. All right, now, that doesn't mean that the solution's exothermic. This means that whatever I get for my solution, change the sign, and that's how I'll get my reaction. So let's first take a look. The other information that is given is it gives us the specific heat of the solution, and it says to assume the density of the solution is 1 gram per milliliter. So Q of my solution is going to be the mass of my solution. So I added 100 milliliters and 100 milliliters, and so I have 200 milliliters. If each milliliter is a gram, I have 200.0 grams of solution times the heat capacity, and you notice that this is on a joule per gram. So that's why I want grams here. It could have been joules per mole, in which case you'd have to have moles here. You've got to be careful with that. And a delta T, so we're using MCAT. A delta T doesn't matter whether you are in Kelvin or Celsius. So I've got 30.1 minus 23.5. And so Q of the solution is 5.544 times 10 to the third joules, right? Because the heat capacity is in joules. So that means that Q of my reaction, so my surroundings gained heat, that means my reaction lost heat, so it's going to be equal in magnitude but opposite in sign. So increase in temperature of the surroundings, heat was released to the surroundings by the reaction. If the reaction releases heat, it's exothermic. Okay, so that's the first one. Calculate the heat released in the reaction. That's implied in the words, but I always like to provide the signs. Now it says calculate the enthalpy change in kilojoules per mole of reaction. Well, that means that I have to determine let me get a good color here. There we go. I have to determine my limiting reagent. So if I've got 100 milliliters of a 1 molar solution, I have 0.10 moles of NaOH. And I also have 0.10 moles of H2SO4. Well, I need, if I correctly balance my equation there, I need 2 moles I need twice as many moles of NaOH as I have H2SO4. And I don't have that. The other thing you can do is divide those by the coefficients. For NaOH, it's 0.5. For the H2SO4, it's 0.1. Pick the smaller. That's your limiting reagent. So that's the other thing if you didn't see that as the limiting reagent. And so that is going to be what I will use to determine my moles of reaction. So let me, now that I've hopefully proved to you that NaOH is my limiting reagent, let's figure out, and some of you already intuitively know that we found our moles of reaction, but I want to do that a little bit more explicitly. Sorry, this eraser is not working well for me. Okay, so I have 0.10 moles, and really I've got more sig figs than that. I'll deal with that at the end. I should have 2 sig figs from my temperature. Okay, so moles of NaOH times 1 mole of reaction. So for every 6.02 times 10 to the 23rd times that the reaction proceeds, it will consume 2 moles of NaOH. So I have 0.05 moles of reaction. So to find my enthalpy for the reaction, I have to take, so my delta H for my reaction is going to be minus 5.544 times 10 to the 3rd joules over 0.05 moles. Okay, and when I do that math, I'm running out of room here, but I'll circle that. My final answer was 110 kilojoules for every mole of reaction. Okay, so that's how you would do types of calorimetry. Remember, just like the amounts of products that form are dictated by our limiting or are limited by our limiting reactant, so too is our heat released or absorbed, limited by the limiting reactant. Okay, I hope this helped you a bit. Have a good day. Thanks for joining me.